Now in nucleophilic substitution, what is happening is that we have a nucleophile. This nucleophile is reacting with the a negative charge. So that compound having from the carbon. There is a substitution of the nucleus. The halogen atom is moving out as a leaving group. So since there is a substitution of a nucleophile, this type of reactions is known as nucleophilic substitution reaction. And this is one of the most important classes of organic reactions of alkyl halides, in which halogen is bonded to sp3 hybridized carbon. So let us see some of the common for nucleophilic substitution. General nucleophilic reaction is Rx plus Nu giving Rnu plus X. So here we can see if we are taking NaOH as a reagent, what will be the negative part in that? It is going to be OH minus. So we will substitute in the compound. So we get ROH as the product. Now if we are taking water as the reagent, we can say that the nucleophile is water because it has bond pairs present on it, and again we get ROH over here. Now NaOR minus, so there we will be getting OR minus or OR dash minus. So there the OR group is going to substitute with the R group, so we are getting ROR. Now the next one is NaI. So there the negative part is I minus, so that is getting substituted to the alkyl halide, so it is R. Minus is going and substituting over there to give us RNH2. Now let us take the next set, RR dash NH. So there also the same thing is going to happen. The H plus is going to move out and the remaining part is the negative part, so that is going to get substituted over there. Now KCN, this is an important part, very important part from here. KCN, AgCN, KNO2 and AgNO2. So here we can say if we have KCN, then the nucleophile is Cn and it is getting substituted as RCN. Whereas if we take AgCN, again the nucleophile is RCN, but now the part is NC minus. In A and in KCN it is Cn minus. So this type of compounds where both the atoms have equal chances of giving rise to a negative charge, this is known as ambidentate nucleophiles or ambident nucleophiles. So here what is happening, we get RNC, that is isocyanide over here, and if we have KNO2, it is going to give us RONO, and AgNO2 is going to substitute to give RNO2. So this is the important part over here, and another important one is regarding LiAlH4. It is a good hydrogen providing agent, as a result of which we get RH over here. So let us see the reaction, let us see about ambidentate nucleophiles here. Ambident nucleophiles, groups like cyanides and nitrides, they possess nucleophilic centers. If we take cyanide, we have carbon and nitrogen as the nucleophilic center. Two contributing structures cyanide ion. Linking through the carbon atom can result in the formation of alkyl cyanides, and through nitrogen atom can lead to isocyanides. Similarly, the nitride ion is also representing a ambidentate nucleophile with two different points of linkage. We have oxygen as one linking atom, and also we have nitrogen as another linking atom. So this is about ambidentate nucleophiles, and this is a example which is given in NCERT, which is asking haloalkanes reacts with KCN to form alkyl cyanides as the main product, while AgCN forms isocyanides as the chief product. What is the reason? KCN is ionic, and as a result they are producing cyanide ions in the solution, whereas AgCN is covalent and carbon Ag is forming a bond. So the nitrogen is free to donate the electron pair, and as a result of which it is going to form. So now let us see the general pathway, or we can say the reactivity order of nucleophilic reaction. We have two types of nucleophilic reaction. One is known as SN1 reaction and another is known as SN2 reaction. SN1 reaction means it is unimolecular reaction and SN2 means it is bimolecular reaction. We will be discussing about all the types of reactions, what is electrophilic substitution, what is nucleophilic substitution, etc. in the end in a separate video. So the stereochemical aspects of this chapter, that is the nucleophilic substitution reaction, will be taken up in that particular video, so that we can have this chapter as a small chapter and easy to learn all the reactions together. So for the time being, we have to understand these two orders. For SN2 reaction, remember it is a bigger reaction, right? SN2 reaction is somewhat a bigger reaction, and there the order is primary greater than, secondary greater than, tertiary. Primary greater than, secondary greater than, tertiary. And for SN1 reaction, the order is going to be tertiary greater than, secondary greater than, primary. So these two orders are important. And another important order is given over here for alkyl halides. This is the order for both SN1 and SN2. This is the order. Ri is having the maximum reactivity towards any of the nucleophilic substitution reaction, followed by RBr, followed by RCl, and least is for RF. So this is also important. So these three orders are important from this section. So here we have a question based on that. In which of the following pairs of halogen compounds which would undergo SN2 reaction faster? Each of the following pairs we have to find which of these is undergoing SN2 reaction faster. So the first one, we can see it is a primary and this is a secondary. So we have already studied that primary will undergo SN2 reaction faster, so this should go faster. Now the next one, we have iodine and chlorine, so iodine will go faster. Now let us move on to the second type of reaction, that is known as elimination reaction. And here what is happening is we are having beta elimination. We have already studied about what is beta elimination. And here we have to study a rule which is known as Zaitsev rule. So let us see what is Zaitsev rule. In dehydrogenation, dehydrohalogenation reactions, the preferred product is that alkene which has greater number of alkyl groups attached to the doubly bonded carbon atoms. Now what does that mean? On which side of the double bond are we having maximum number of alkyl groups? That is going to be the major product. So if I take over here, we can see 2 on the right side and 3 on the left side, and here we can see 1 on the right side and 4. So this is lesser, right? So since this is lesser and this is more balanced. Here it is like more balanced, but here it is less balanced on the either side. So this is going to be the major product and this is going to be the minor product. So that is what is known as Zaitsev rule. We have to balance it, right? Having almost equal number of methyl groups substituted on both sides, then we can say it is the major product. So this is known as Zaitsev rule. Now the next one is reaction with metals. Now here we have to talk about Grignard reagent. Now first of all, we have CH3CH2Br. This is reacting with magnesium in the presence of dry ether to give us CH3CH2CH MgBr. This is known as Grignard reagent, whose general formula is RMgX. Now this RMgX, in this, the positive charge goes to the magnesium, negative charge go to R and X. When we are hydrolyzing RMgX, we will be getting an alkane and also we get MgOH. So we have to keep it in moisture free environment. The reason being, it reacts readily with water, and as a result of which we get alkanes and this particular product. Now when does this particular Grignard reagent react? Grignard reagent reacts when there is presence of active hydrogen. That is, when there is presence of acidic hydrogen. If we have water, we can say we have H plus and OH minus, and this H plus is known as an acidic hydrogen, and this can react with the Grignard reagent. So this is Grignard reagent R, Mg and X. So what is happening is that this positive charge, this is having the negative charge, right? So this part is going to go with the negative part, that is MgOH, and this is also having a negative part, so this is moving out as MgOHx, and to the negative side we are going to add the positive charge, so it is going to be RH over here. Now if I take another example, if we have amines RMgx plus NH2, we can take RNH2, so it is R plus NH2 minus, so this is the positive side and this is the negative side, so these two are going to react, we get RR dash and we get MgNH2x. So these are products that we are getting over here. Now let us move on to the last reaction over here. This is known as Wood's reaction. Alkyl halide reacts with sodium in dry ether to give us hydrocarbons, which is having double the number of carbon atoms, and this is known as Wood's reaction. We have studied lots of things regarding Wood's reaction in the chapter of hydrocarbons. So comment below what are the abnormal products of Wood's reaction. Comment below what are the abnormal products of Wood reaction, and also you have to comment what is the intermediate. What is the intermediate of Wood's reaction, or what is the pathway of Wood's reaction? Is it electrophilic, is it free radical, or is it any other mechanism? This also you have to comment below. Now let us see the reactions of haloarenes. The first one is nucleophilic substitution. Aryl halides are extremely rare, or we can say less reactive towards nucleophilic substitution reaction. First reason is because of the partial double bond character, that is due to resonance effect. Second one is the difference in hybridization of the carbon atom. Here we have sp2 hybridized carbon, whereas if we take a haloalkane, that is going to be sp3 hybrid carbon. So we have difference in the hybridization, that can also be a reason. Third important reason is the inability of the phenyl cation, and the last important reason is because of steric hindrance, or we can say steric repulsion. Now let us see the first reaction, where we are going to react this compound with NaOH in the presence of H plus at 623 Kelvin and 300 atmosphere. So then what is going to happen, this Cl is removed out at this particular condition only, not simply by shaking. So this will be giving OH over here, and we get a phenol here. Now let us see what is the effect of adding or substituting the different positions. So here we have an para substituted, and here we have an ortho and para, and here we have all the ortho and para, one ortho and para, and here we can see both ortho and para position is substituted. So here what is going to happen, this is a electron withdrawing group, NO2. So electron withdrawing group is occupied at the ortho and the para position, and this is going to increase the reactivity of haloarenes. So here we can say 443 Kelvin was needed for substituting this OH, but now 2 NO2 are there, so reactivity is increased further, and as a result of which lesser temperature is needed. And if we are taking 3 NO2 groups at ortho and para positions, then what is going to happen, we just have to take the warm solution and just shake it well to get the product, because that is maximum reactive among these three. So they can ask the order of reactivity as well, so this is important. Now let us move on to the electrophilic substitution reaction. The first one is known as halogenation. Now in halogenation, we have already studied in the hydrocarbons chapter that the reagent used is Cl2 in the presence of anhydrous FeCl3. So we will be getting an ortho product and para product and also an ortho product. Always remember, para is the major product. Para is always the major product. Now for nitration, we are taking HNO3 in the presence of concentrated H2SO4. We will be getting ortho as the minor product and para as the major product. In sulfonation, we are taking concentrated H2SO4, or even we can use oleum. So we will be getting minor product as the ortho product and para product is the major product. Now in Friedel-Crafts alkylation reaction, we are taking CH3Cl in the presence of anhydrous AlCl3 to get ortho and para products. And in the case of acylation, we are taking this compound, that is acyl chloride, in the presence of anhydrous AlCl3 to get a minor ortho product and a major para product. Let us move on to the last reaction of haloarenes, which is reaction with metals. Now the first reaction is known as Wurtzwittig reaction. where we are taking one molecule of an aryl halide and one molecule of an alkyl halide and treating it with sodium in the presence of ether. In this particular reaction, we will be getting this particular compound because we have taken one aryl halide and we have taken two molecules of sodium and we have also taken an alkyl halide. So this much part is moving out and this R is getting substituted over here. So we will be getting this as our major product. Now let us move on to phytic reaction. Phytic reaction is also similar to the Woods reaction. Here what is happening, instead of Rx we are taking ARX, that is aryl halide. So when we take two molecules of aryl halide, this is first molecule, we have two molecules of sodium and we have another molecule of aryl halide. So when we are taking another molecule, this much part is moving out as 2NaX and these two are going to join together to form diphenyl. So this completes the theory of this chapter. Now let us discuss some of the important questions related to this particular section. So let us start with the first question. Which of the following reactions is an example for nucleophilic substitution reaction? So we have already seen this in the table. So this is the example for nucleophilic substitution reaction. Let us see the second one. What products are formed when the following compounds are treated with Br2 in the presence of FeBr2? So here we can see we have two CH2 groups here. So with respect to CH3, we have to find which is the ortho and para directing groups. So here we can say this bromine is ortho with respect to this and ortho with respect to this. But this is para with respect to this, but we do not have a para with respect to this. So this cannot be the answer. Now, this is para with respect to this, but this is ortho with respect to this. So one is ortho and one is para. And with respect to this, we have an ortho here. And with respect to this also, it is ortho. So that is not possible. We should get both ortho and para. So here what is happening, with respect to this is ortho. And with respect to this is para. And with respect to this is going to be para position. And to this is going to be ortho position. So both are orthopara and orthopara. So this should be the answer. Which of the following biphenyl is optically active? Now, due to steric hindrance arising due to the presence of bulkier groups at the ortho positions, the biphenyl system is always non-planar, that is, it is optically active. So this should be the answer. Now, we have to say when is this particular reaction fastest. So if you could recall the SN1 and SN2 reaction, this is an example for SN2 reaction. And if you don't know, we will be discussing this section in a separate video where we will discuss about the different types of organic reactions. So this is an SN2 reaction, and the condition for SN2 reaction is that it should be in a polar aprotic solvent, that is NN dimethyl formamide. Next, which of the following is a secondary alkyl halide? So if we take, this is a primary, this is also primary, this is also a primary, so this should be the secondary one. Which of the following may be classified as an aryl halide? Aryl halide is that onto which the chlorine is attached directly to the benzene ring, and so this is the answer. Which of the following is correct for the reaction? We have HBr in the presence of peroxide. Since we have peroxide, it is going to be anti-Markovnikov's addition. Now the next one is we have CH3 in the presence of Cl2 and H nu. We are getting P. We have to find what is the product P. Now we are getting 3 as the answer because it is CH3 present over here. So we have to substitute one of the hydrogen with a chlorine. Now here we have to treat this molecule with Br2 in the presence of H nu. So here also we can follow the same method, but here there is a problem. We have a free radical pathway, so we have to create a free radical, that is this. So onto this free radical we have to substitute the bromine, and as a result of which we are getting this as the answer. So the answer is option number 3. Which of the following is the most stable? Here you can see this is a conjugated system. What is conjugated? We have a double bond followed by a single bond. So this is known as a conjugated system. Double bond, single bond, double bond, single bond. This is known as a conjugated system. And in conjugated free radicals, we have resonance, and resonance stabilization make this as the most stable among all the options. Now let us see the next question. C6H5CH3 in the presence of Br2 and FeBr3. This is an example for electrophilic reaction which we have already studied. Now this question we have to react it with KOH. So what is happening? We have to substitute it with OH, but this is an example for SN2, and in SN2 there is inversion of configuration, as a result of which its structure is changing. So this is SN2. Next, CH3 thrice Br is treated with KOH. So at that time we are having beta elimination. Bromine will go from this carbon and hydrogen is going to go from the next carbon, that is here. So there is a double bond formed over here. So this is the compound that we're getting, and now we have to carry out the anti-Markovnikov addition because R2O2 is an organic peroxide. R2O2 is an organic peroxide, so we have to carry out anti-Markovnikov addition, and after anti-Markovnikov addition, the bromine is substituted. This is deficit in hydrogen, that is we are getting this particular product. Sorry, bromine is added to that part which is excess in hydrogen, so this is the product. And in Markovnikov addition, if there was no organic peroxide, we will be adding bromine to that part which is having lesser number of hydrogen atoms. And now let us move on to the last question of today's lecture. This is the question. We have to treat this alcohol with SOCl2. So we will be getting chlorine substituted in the place of OH, that is this. And now we have to treat it with KCN. So CN will be substituted in the place of chlorine, and because it is SN2 mechanism. And after that, what is happening? We are going to treat it with H plus, and that time we are going to get an acid, that is CH2COOH. So the answer is option number 3. So with this, we are concluding the chapter Halo. In the next lecture, we will be discussing the chapter alcohols, phenols and ethers. So see you again in the next lecture. Till then, goodbye and happy learning.